Dark matter often sounds confusing because the name suggests something strange or unknowable. In reality, the idea grows out of very ordinary observations about motion and gravity. Nothing about it starts with mystery for its own sake. It begins with careful measurement and a simple question: does what we see account for how things move? Consider a galaxy as a vast system of stars orbiting a common center. Gravity provides the attraction that keeps those stars bound together. By measuring how fast stars move at different distances from the center, it becomes possible to estimate how much mass must be present. This approach works reliably for familiar systems, such as planets around the sun. When astronomers applied the same reasoning to galaxies, something unexpected appeared. Stars far from the center moved much faster than a visible matter could justify. The stars' gas and dust that telescopes revealed did not provide enough gravitational influence to explain the motion. The galaxy behaved as though it contained much more mass than could be seen. At first, this seemed like a measurement problem. Instruments improved, data sets expanded. The result remained. The same mismatch appeared across many galaxies, and later in large collections of galaxies. Motion consistently pointed to additional mass spread well beyond the bright regions. At that point, the issue could not be dismissed. Either gravity behaved differently on large scales, or a large amount of matter influenced motion without interacting with light. Dark matter enters as a name for that missing influence. The term does not describe what it is made of. It describes how it behaves. It refers to whatever produces gravitational effects without emitting or absorbing light. This way of thinking fits naturally within physics. Physical existence does not depend on visibility. It depends on measurable influence. Long before air was understood, its effects on motion and pressure made its presence undeniable. Dark matter occupies a similar logical role, though on cosmic scales. Evidence extends beyond galaxy rotation. Light passing near massive clusters bends more than visible matter alone predicts. The large-scale structure of the universe forms in ways that require additional gravitational influence early in cosmic history. Each observation points to unseen mass shaping space and motion. A deeper question follows naturally. Does this unseen influence come from a new kind of matter, or does it signal a need to revise how gravity behaves across vast distances? Both ideas aim to explain the same observations. Understanding dark matter begins with accepting that gravity responds to mass whether that mass shines or not. Following that influence carefully leads deeper into how matter, gravity, and the structure of space itself fit together. Following that influence leads straight into how dark matter becomes more than a label and turns into a measurable part of modern physics. One of the clearest moments came in the 1970s through the work of astronomer Vera Rubin, working with Kent Ford. Rubin studied how stars move within spiral galaxies. According to gravitational reasoning that works everywhere else, stars farther from the center should move more slowly, much like distant planets around the sun. What Rubin found refused to follow that expectation. The outer stars moved at nearly the same speed as inner ones. The motion traced a flat curve rather than a declining one. That result carried a sharp implications. Either gravity changed its behavior at galactic scales, or far more mass surrounded the galaxy than telescopes revealed. Rubin's careful measurements, repeated across many galaxies, pushed the idea of unseen mass from speculation into necessity. From there, the concept grew stronger through independent methods. One of the most striking involves how massive objects bend light. Einstein's description of gravity predicts that mass curves the paths of light traveling nearby. Astronomers use this effect, called gravitational lensing, to map where mass resides. In the early 2000s, observations of a system known as the Bullet Cluster, analyzed by Douglas Clow and collaborators, showed something remarkable. Ordinary matter, visible as hot gas, slowed and piled up after a collision between two galaxy clusters. The gravitational influence traced by lensing appeared somewhere else entirely. The dominant mass passed through with little interaction. That separation mattered. It showed that the unseen mass behaved differently from familiar matter. It clumped gravitationally, yet barely interacted through collisions or light. Gravity revealed its presence even where visible matter lagged behind. These observations point toward what dark matter represents at a fundamental level. Dark matter functions as a source of gravity that interacts very weakly, if at all, through other known forces. It contributes mass energy to space, shapes motion, and influences how structures form, while remaining largely indifferent to light, heat, and ordinary collisions. This challenges everyday assumptions deeply. In daily life, matter announces itself through sight, touch, resistance, or heat. Mass seems inseparable from substance you can point to. On cosmic scales, that intuition breaks down. Motion responds to gravity alone, not to visibility. A star follows the gravitational landscape laid out by all mass present, regardless of whether that mass glows. Physicists model dark matter using this principle. Instead of asking what it looks like, they ask how much gravitational influence appears necessary at each location to account for observed motion and lensing. Computer simulations then distribute dark matter in extended halos around galaxies and clusters. When these models evolve forward in cosmic time, they reproduce the large-scale structure seen in surveys, filaments, clusters, and voids arranged in a vast web. This success matters. It shows that treating dark matter as a real component of the universe leads to consistent predictions across independent observations. The same invisible mass explains galaxy rotation, cluster dynamics, lensing maps, and the growth of structure from the early universe. At the deepest level currently accessible, dark matter represents mass that participates fully in gravity while remaining largely disconnected from electromagnetic processes. It behaves as matter in the gravitational sense, contributing to how space responds and how motion unfolds, without behaving like atoms, gas, or dust. That realization reshapes how matter itself gets defined. Matter no longer requires visibility, solidity, or chemical structure. Gravitational influence becomes the defining feature. If something shapes motion persistently and consistently, physics treats it as real. This view also explains why dark matter fits naturally into descriptions of space and time. Gravity responds to energy and mass, regardless of form. Space curves, and motion responds based on total content, not on what that content looks like. Dark matter enters those equations seamlessly because gravity already accounts for unseen contributors. What remains uncertain concerns composition. Many candidates exist, ranging from new elementary particles to more complex possibilities. Experiments search for rare interactions deep underground, in particle accelerators, and through astrophysical signals. None have yet delivered a definitive answer. What remains firm lies in the gravitational evidence. Dark matter, at this stage, stands as a measured component of the universe, inferred through multiple independent techniques. It represents how much mass must exist for space, motion, and structure to behave the way observations show. Understanding it means accepting that the universe carries substance beyond what eyes and instruments tuned to light can reveal, and that gravity serves as the guide, linking the unseen to everything that moves within it. As dark matter takes its place within physical descriptions, its consequences begin to appear across many areas at the same time. Observations that once felt isolated start to support each other, and familiar ideas about matter, structure, and influence lose their apparent simplicity. The large-scale arrangement of the universe offers one of the clearest examples. Galaxies do not scatter randomly. They collect along immense filaments, surround vast empty regions, and assemble into clusters connected by long strands of mass. Early attempts to explain this structure using only visible matter ran into a timing problem. Ordinary matter, interacting strongly with radiation in the early universe, could not gather quickly enough under gravity to form the structures observed today. Introducing dark matter resolves this tension naturally. Dark matter begins clumping early, before atoms form and before light moves freely through space. It supplies gravitational wells that deepen over time. Ordinary matter later falls into these wells, cools, and forms stars and galaxies. Structure develops in a sequence that matches observation without repeated adjustments. From this perspective, galaxies appear less like independent systems and more like visible highlights tracing an underlying framework. Their shapes, motions, and distributions reflect a deeper mass arrangement that remains unseen. This leads to an unexpected reversal of intuition. Human senses treat visible matter as dominant because it announces itself. On cosmic scales, gravity responds to total mass regardless of appearance. The universe organizes itself according to what contributes gravitational influence, not according to what emits light. Time itself enters the story in a revealing way. The timeline of cosmic evolution aligns far more smoothly when dark matter is included. Small density differences present early on grow at rates consistent with observation. Galaxies form neither too early nor too late. Clusters assemble when expected. A single additional component resolves multiple chronological puzzles at once. Gravitational lensing reinforces this unified picture. Light bends when passing through regions of mass, allowing astronomers to map where gravitational influence resides. These maps repeatedly show mass distributed beyond the boundaries of visible matter. Extended halos surround galaxies and clusters, revealing smooth mass distributions without sharp edges. Here, everyday reasoning begins to fail. Mass feels naturally tied to compact objects with clear boundaries. Dark matter spreads over large regions, forming halos that resist collapse into dense structures. This distribution explains why galaxies remain bound even when their stars move rapidly. The motion reflects the presence of an extended gravitational environment rather than a concentrated core. Another tension arises from how dark matter interacts. In ordinary matter, interactions leave traces: heat, light, friction, radiation. Dark matter interacts powerfully through gravity while remaining almost indifferent to other forces. During collisions between galaxy clusters, ordinary gas slows and heats, while dark matter continues onward, detectable only through its gravitational influence. This challenges assumptions about interaction and causality. Influence often feels inseparable from exchange. Dark matter demonstrates that gravity alone suffices to connect systems and shape motion without exchanging light or heat. Causality remains intact because influence still propagates through space, even if it does so through a single channel. A broader picture emerges. The universe resembles a gravitational network in which different components participate differently. Ordinary matter interacts richly through many forces, but contributes modestly to gravity on large scales. Dark matter contributes strongly to gravity while interacting weakly otherwise. Each component shapes cosmic behavior through its own interaction profile. Early skepticism treated dark matter as a placeholder for error. Over time, mismatches appeared repeatedly and independently. Galaxy rotation, lensing, cluster dynamics, and structure formation all pointed toward the same missing contribution. Adding dark matter did not patch individual discrepancies. It revealed a shared cause. This coherence explains why dark matter remains difficult to detect directly. Instruments designed to capture light or heat cannot register something that barely engages with those processes. Its presence must be inferred through motion, lensing, and large-scale structure. Physics already relies on inference in many domains. Gravity itself announces its existence only through effects. This reliance on inference carries an important implication. The universe does not restrict itself to what human senses evolved to detect. Perception samples a narrow band of reality. Physics expands that band by following consistent effects wherever they lead, even beyond direct observation. Dark matter also reshapes how space itself is understood. Gravity links mass energy to the geometry of space-time. If most mass resides in dark matter, then large-scale curvature reflects that unseen contribution. The paths galaxies follow, the way light bends, and the formation of structure all depend on it. This places dark matter at the center rather than the margins of cosmology. The universe responds primarily to what weighs the most, not to what shines the brightest. Computer simulations highlight this point vividly. Models that include dark matter evolve into structures resembling observed surveys, complete with filaments, clusters, and voids. Models that exclude it fail in systematic ways. Structures appear late, thin, or incomplete. Each failure points back to the same missing ingredient. Viewed individually, these observations might invite separate explanations. Taken together, they form a consistent narrative. Motion, lensing, timing, and structure all trace the same gravitational influence. The meaning of dark matter extends beyond accounting for missing mass. It indicates that physical reality includes components operating outside direct detection, shaping outcomes through long-term, large-scale influence. This does not diminish ordinary matter. It places it within a wider context. Stars and planets become visible expressions of deeper gravitational organization. What shines follows what weighs. Understanding dark matter in this way changes how explanation itself works. Instead of relying on appearance, physics relies on convergence. Multiple independent measurements pointing toward the same unseen cause outweigh the absence of direct detection. Dark matter connects gravity, motion, space, and cosmic history into a unified framework. Each reinforces the others. What once appeared as scattered anomalies now reads as different perspectives on the same underlying structure. That realization carries an important implication. The universe remains intelligible even when much of it lies beyond immediate perception. Careful attention to effects leads to coherence rather than confusion. Dark matter does not sit alongside the story of the universe. It runs through it, shaping how matter gathers, how structures form, and how motion unfolds across vast distances. Understanding that thread transforms many isolated puzzles into a connected picture, revealing a universe that proves larger, yet no less ordered than it first appears. When all the pieces are viewed together, dark matter settles into a clear role rather than remaining a loose hypothesis. It provides a consistent way to understand how the universe behaves on the largest scales, tying motion, structure, and stability into a single picture supported by many observations. Galaxies rotate as they do because they sit inside extended regions of unseen mass. Clusters remain bound because additional gravitational influence surrounds them. Light bends along paths shaped by more mass than telescopes reveal. Large-scale structure forms early and grows in the right way because extra gravitational influence shapes space long before stars appear. Together, these facts reinforce one explanation. This convergence marks what physics treats as firmly established. A substantial amount of matter contributes gravitationally across the universe while remaining largely invisible to light and ordinary interactions. Its presence is inferred through motion, lensing, and structure, and those inferences agree across different methods, scales, and eras. Removing this component breaks that agreement. Including it restores consistency. What remains uncertain lies in the details rather than the existence. The exact nature of dark matter remains unknown. Its composition, internal properties, and origin resist direct detection. Experiments search for rare interactions. Observations probe subtle effects. The absence of a definitive identification sets the boundary of current knowledge. This balance between confidence and uncertainty matters. Dark matter does not represent a missing piece filled in by guesswork. It represents a component required by evidence, even as its deeper description remains incomplete. Its strength lies in how many independent observations it unifies without contradiction. Including dark matter reshapes how stability itself is understood. Systems remain intact not only because of what shines within them, but because of what weighs around them. Motion responds to total gravitational influence, not to visibility. Structure follows mass, whether that mass announces itself or not. This perspective alters how familiar scenes are interpreted. The night sky no longer appears as a collection of isolated lights scattered across emptiness. Each bright point traces a deeper gravitational environment shared with countless others. What can be seen marks only a fraction of what governs motion and form. Dark matter also clarifies why the universe remains intelligible. The same principles explain galaxies, clusters, and cosmic structure without changing rules from one scale to another. Gravity responds consistently. Motion follows predictably. Stability emerges naturally. The practical takeaway rests here. Reality extends beyond direct detection, and physics follows influence rather than appearance. Some of the most important contributors to how the universe behaves do not announce themselves through light, heat, or touch. They reveal themselves through what they shape over time. Understanding dark matter encourages a broader view of existence. What matters most is not always what stands out, but what holds everything else together. The universe evolves under the guidance of influences that operate indirectly yet persistently, shaping motion, structure, and history across vast distances. Seen this way, dark matter stops feeling distant or abstract. It becomes part of the framework that allows galaxies to form, motion to remain stable, and the universe to develop structure at all.
Ladies and gentlemen, let me begin with a confession. Nobody, and I mean nobody, truly understands quantum physics. Now relax, that's not an insult to your intelligence. It's a compliment to your courage for being here anyway. Because tonight we're not here to master quantum mechanics. We're here to stop being afraid of it. We're here to see that it isn't mystical nonsense, nor incomprehensible math magic. It's simply nature behaving in a way we didn't expect. And that's where all the fun begins. Look around you. The chair you're sitting on feels solid. The floor feels real. Your body feels like a well-defined thing with edges. This makes sense because at our scale, the universe follows rules that are polite, predictable, and mostly reasonable. But shrink yourself down, smaller than a cell, smaller than an atom, smaller than the nucleus, and suddenly the universe stops being polite. It starts misbehaving. At the quantum level, particles don't behave like tiny billiard balls. They don't have neat positions and well-defined paths. They don't even agree to exist in just one place at a time. Instead, they behave like possibilities. Not maybes in the philosophical sense, but real, measurable, mathematical possibilities that interfere with one another like ripples on water. This is the first shock. Nature is not made of things. It is made of probabilities. Now let me warn you about something very important. If at some point you think, "Oh, I get it now," you almost certainly don't. And that's perfectly fine. Quantum physics is not about building comforting mental pictures. It's about accepting that the universe is under no obligation to make sense to our intuition. Our intuition evolved to throw rocks, not to understand electrons. So what is quantum physics? At its heart, quantum physics is a set of rules that tells us how the smallest pieces of reality behave. And those rules are weird in three essential ways. Things come in chunks. Things can be in many states at once. Observing something changes it. Each of these will attack your common sense in a different way. And by the end of this talk, your common sense will be bruised, but still standing. Let's start with the first rule. Things come in chunks. In the everyday world, change feels smooth. You can dim a light gradually. You can pour water continuously. You can walk halfway across a room. But at the quantum level, nature says, no, you get this amount or that amount, nothing in between. Energy comes in packets called quanta. That's where the word quantum comes from. An electron in an atom can only have certain energies, like a staircase, not a ramp. It cannot exist between steps. You can't negotiate with it. This isn't a limitation of our measuring devices. It's a limitation written into reality itself. Nature runs on discrete pixels, not analog film. Now, the second rule is where things get truly unsettling. A quantum object can exist in multiple states at once, not metaphorically, not symbolically, literally. An electron can be here and there. A particle can go through two paths simultaneously. A system can be in conflicting states until something forces it to choose. This is called superposition. And no, it doesn't mean the particle is secretly hiding its true position. It means the concept of having a single position does not apply until interaction occurs. Reality is fuzzy until it is asked a question. This brings us to the most dangerous word in quantum physics, observation. Observation doesn't mean a human staring dramatically at an experiment. It means interaction. When a quantum system interacts with the world, when information is exchanged, the superposition collapses into a definite outcome, not because the universe cares about consciousness, but because interaction destroys ambiguity. Nature doesn't like undecided situations once information leaks out. And here's the uncomfortable truth. You cannot observe the quantum world without disturbing it. This is not a technical problem. This is not a flaw in our instruments. This is how reality works. At the quantum level, to know is to interfere. Now pause and let this sink in. The universe is not a static machine ticking along independently of us. It is a dynamic process where questions shape answers. This doesn't mean reality is subjective. It means reality is participatory. And that idea, right there, changes how we think about everything. All right, now we arrive at the experiment that refuses to stay quiet. If quantum physics were a courtroom drama, this would be the piece of evidence that makes everyone shift uncomfortably in their seats. It's called the double-slit experiment. And I promise you this, if you understand this experiment, even emotionally, you understand the heart of quantum physics. Imagine a simple setup. You take a wall, you cut two narrow slits in it. Behind the wall, you place a screen that records where particles land. Now let's fire particles, electrons, one at a time toward the wall. Not waves, not a beam, one single electron at a time. Common sense says each electron should go through one slit or the other, hit the screen, and slowly build two piles behind the slits. That's how tiny bullets behave. But electrons are not tiny bullets. When you run the experiment, something outrageous happens. After many electrons pass through, a pattern appears on the screen, a pattern of alternating bright and dark bands. This is an interference pattern. And interference patterns do not come from particles. They come from waves. But here's the problem. We fired the electrons one at a time. Each electron somehow interferes with itself. Let that sink in. There is no second electron to interfere with. There is no crowd effect. There is no hidden companion. Each individual electron behaves as if it went through both slits at once, spread out like a wave, interfered with itself, and then landed as a single dot, not halfway, not smeared, one clean impact. Wave behavior during travel, particle behavior during detection. This is not philosophy. This is what the experiment shows. Now at this point, a reasonable person says, fine, the electron is a wave. So we get clever. We place detectors at the slits to see which slit the electron goes through. And the moment we do that, the interference pattern disappears. We get two boring piles. No waves, no drama, just particles. Nothing about the setup changed except one thing. We asked the electron a question. Which path did you take? And the electron answered by behaving differently. Not because it got shy, not because it noticed us, but because path information entered the universe. Once a universe knows which slit, the wave behavior is destroyed. This is the core lesson of quantum mechanics. What can happen matters. What is allowed to happen matters. And what information exists matters. Before measurement, the electron explores all possible paths. After measurement, those possibilities are eliminated. Reality does not commit early. It keeps its options open. Now let's be very clear about something. The electron is not deciding. It is not thinking. It is not aware. Quantum mechanics is weird enough without adding psychology to particles. What's happening is simpler and stranger. The electron is described by a wave function, which tells us the probability of every possible outcome. This wave function evolves smoothly, obeying precise mathematical rules, until interaction forces a single result, and then, bang, possibility becomes fact. Here's the part that makes physicists uncomfortable at dinner parties. The wave function doesn't represent our ignorance. It represents real physical possibilities. Until measurement, asking, "Where is the electron?" is like asking, "What note is this symphony playing?" before it reaches the orchestra. The question doesn't apply yet. This is why quantum physics breaks our intuition. We want reality to be like a photograph, static, well-defined, already taken. But reality is more like a live performance. It evolves, it responds, it collapses into outcomes only when interactions demand it. Now you might be thinking, if observation changes reality, does that mean reality depends on us? No, it depends on interaction, not consciousness. A rock can observe an electron. A detector can observe an atom. The universe observes itself constantly. Humans are not special observers. We are just complicated measuring devices with opinions. But make no mistake, this changes how we think about cause and effect. In classical physics, causes come first, effects come later. In quantum physics, the set of possible outcomes comes first, and the actual outcome appears only at the moment of interaction. Nature doesn't roll dice in advance. It rolls them when forced to.
Now, just when you think quantum physics couldn't possibly get stranger, it does something that seems downright rude. It breaks distance. Up until now, at least one comforting idea survived. Things affect nearby things. Causes travel through space. Quantum mechanics looks at that idea and shrugs. Let me introduce you to entanglement. Entanglement happens when two particles interact in such a way that their properties become linked, not correlated like matching socks, but inseparably connected. Once entangled, you can no longer describe one particle independently of the other. They are no longer two systems. They are one system with two locations. Here's a simple way to think about it. Imagine I give you two boxes and ship one to the other side of the galaxy. You open your box and find a red ball. You instantly know the other box contains a blue ball. That's boring. That's classical correlation. Quantum entanglement is not like that. In quantum mechanics, the balls don't have colors until you open the box. Before measurement, the system is in a superposition of red here / blue there, blue here / red there. Neither outcome exists yet. But the moment you open your box, the other box, no matter how far away, is instantly determined, not because information traveled faster than light, but because there was never separate information to begin with. Einstein hated this. He called it spooky action at a distance, and he was convinced quantum mechanics must be incomplete. Surely, there must be hidden variables, secret instructions carried by the particles. So physicists tested it again and again and again. Reality took quantum mechanics' side every time. The experiment...
Ladies and gentlemen, let me begin with a confession. Nobody, and I mean nobody, truly understands quantum physics. Now relax, that's not an insult to your intelligence. It's a compliment to your courage for being here anyway. Because tonight we're not here to master quantum mechanics. We're here to stop being afraid of it. We're here to see that it isn't mystical nonsense, nor incomprehensible math magic. It's simply nature behaving in a way we didn't expect. And that's where all the fun begins. Look around you. The chair you're sitting on feels solid. The floor feels real. Your body feels like a well-defined thing with edges. This makes sense because at our scale, the universe follows rules that are polite, predictable, and mostly reasonable. But shrink yourself down, smaller than a cell, smaller than an atom, smaller than the nucleus. And suddenly the universe stops being polite. It starts misbehaving. At the quantum level, particles don't behave like tiny billiard balls. They don't have neat positions and well-defined paths. They don't even agree to exist in just one place at a time. Instead, they behave like possibilities, not maybes in the philosophical sense, but real, measurable, mathematical possibilities that interfere with one another like ripples on water. This is the first shock. Nature is not made of things. It is made of probabilities. Now let me warn you about something very important. If at some point you think, "Oh, I get it now," you almost certainly don't. And that's perfectly fine. Quantum physics is not about building comforting mental pictures. It's about accepting that the universe is under no obligation to make sense to our intuition. Our intuition evolved to throw rocks, not to understand electrons. So what is quantum physics? At its heart, quantum physics is a set of rules that tells us how the smallest pieces of reality behave. And those rules are weird in three essential ways. Things come in chunks. Things can be in many states at once. Observing something changes it. Each of these will attack your common sense in a different way. And by the end of this talk, your common sense will be bruised, but still standing. Let's start with the first rule. Things come in chunks. In the everyday world, change feels smooth. You can dim a light gradually. You can pour water continuously. You can walk halfway across a room. But at the quantum level, nature says, no, you get this amount or that amount, nothing in between. Energy comes in packets called quanta. That's where the word quantum comes from. An electron in an atom can only have certain energies, like a staircase, not a ramp. It cannot exist between steps. You can't negotiate with it. This isn't a limitation of our measuring devices. It's a limitation written into reality itself. Nature runs on discrete pixels, not analog film. Now, the second rule is where things get truly unsettling. A quantum object can exist in multiple states at once, not metaphorically, not symbolically, literally. An electron can be here and there. A particle can go through two paths simultaneously. A system can be in conflicting states until something forces it to choose. This is called superposition. And no, it doesn't mean the particle is secretly hiding its true position. It means the concept of having a single position does not apply until interaction occurs. Reality is fuzzy until it is asked a question. This brings us to the most dangerous word in quantum physics, observation. Observation doesn't mean a human staring dramatically at an experiment. It means interaction. When a quantum system interacts with the world, when information is exchanged, the superposition collapses into a definite outcome, not because the universe cares about consciousness, but because interaction destroys ambiguity. Nature doesn't like undecided situations once information leaks out. And here's the uncomfortable truth. You cannot observe the quantum world without disturbing it. This is not a technical problem. This is not a flaw in our instruments. This is how reality works. At the quantum level, to know is to interfere. Now pause and let this sink in. The universe is not a static machine, ticking along independently of us. It is a dynamic process where questions shape answers. This doesn't mean reality is subjective. It means reality is participatory. And that idea, right there, changes how we think about everything. All right, now we arrive at the experiment that refuses to stay quiet. If quantum physics were a courtroom drama, this would be the piece of evidence that makes everyone shift uncomfortably in their seats. It's called the double-slit experiment. And I promise you this, if you understand this experiment, even emotionally, you understand the heart of quantum physics. Imagine a simple setup. You take a wall, you cut two narrow slits in it. Behind the wall, you place a screen that records where particles land. Now let's fire particles, electrons, one at a time toward the wall. Not waves, not a beam, one single electron at a time. Common sense says each electron should go through one slit or the other, hit the screen, and slowly build two piles behind the slits. That's how tiny bullets behave. But electrons are not tiny bullets. When you run the experiment, something outrageous happens. After many electrons pass through, a pattern appears on the screen, a pattern of alternating bright and dark bands. This is an interference pattern. And interference patterns do not come from particles. They come from waves. But here's the problem. We fired the electrons one at a time. Each electron somehow interferes with itself. Let that sink in. There is no second electron to interfere with. There is no crowd effect.
The greatest obstacle to building a reliable mind isn't lack of effort. It's that most people are building the wrong thing entirely. Watch someone preparing for an examination. They sit with their textbook open, reading the same paragraphs over and over. They copy definitions onto index cards. They highlight sentences until the page looks like a rainbow. Hours disappear into this work. But what's actually being constructed inside their mind? They're creating the illusion of knowledge. The words become familiar. The equations start to look comfortable. There's a warm feeling of recognition when they see the material again. And this feeling is treacherous because it masquerades as understanding. The brain confuses familiarity with comprehension, and the student walks into the examination room believing they know something, only to discover they know nothing at all. Most people treat their minds like storage containers. They pour information in, hoping it will stay there, available when needed. They memorize formulas, collect facts, and believe that repetition will somehow transform these fragments into understanding. But a mind built this way is brittle. It can recite information, it can pass certain tests, but when confronted with a genuinely new problem, something it hasn't seen before in exactly that form, it shatters. The mind that can't fail isn't built through accumulation. It's built through a completely different process, one that looks nothing like what most people call studying. The real test of knowledge isn't whether you can recognize the right answer when you see it. The real test is whether you can generate the answer from nothing, using only the principles you understand. And that requires a fundamentally different kind of structure in your mind. Think about the difference between a photograph and a map. A photograph captures what something looks like from one angle, frozen in time. It's detailed, it's accurate for that specific view, but it's also completely rigid. Change your position slightly, and the photograph becomes useless. A map, on the other hand, is an abstraction. It shows relationships, connections, the underlying structure of a territory. With a good map, you can navigate from any starting point to any destination, even through routes you've never traveled before. Most people build their minds like photograph albums. They collect images of solutions, examples they've seen, problems their teacher worked through on the blackboard. But when they encounter a new problem, a different angle, they're lost. They flip through their mental photographs, looking for an exact match, And when they don't find one, they have nowhere to go. The mind that can't fail is built like a map. It contains principles, not pictures. It understands the relationships between ideas, the deep structure that underlies the surface details. And this kind of mind isn't built through passive absorption. It's built through active reconstruction. Here's the first principle. Never trust that you understand something until you can build it from scratch. Not recite it, not recognize it, but actually construct it, starting from the most basic elements you're certain about. Suppose you're trying to understand why objects fall at the same rate regardless of their weight. You could memorize this fact. You could even memorize the historical story that goes with it. But none of that is understanding. Understanding means you can start from what you know about forces and motion and derive this result yourself. You can explain why a hammer and a feather, in the absence of air resistance, must fall together. You can work through the logic step by step, and if someone challenges any step, you can defend it or discover your error. This is exhausting work. It's much harder than reading and highlighting. It takes 10 times longer, but it builds a completely different structure in your mind. Instead of memorizing a conclusion, you've built the pathway to that conclusion. And that pathway can be used again, in different contexts, to reach different conclusions you've never seen before. Most students read a chapter in their textbook, perhaps once, perhaps twice. They feel they understand it because the logic seems to flow smoothly as they read. The author has done the work of making it clear, but this is deceptive. The clarity belongs to the author, not to the reader. Close the book and try to recreate that explanation from memory, and you'll discover how little actually transferred to your mind. The difference is between watching someone else think and thinking yourself. When you watch someone solve a problem on a blackboard, their solution looks elegant, even obvious. Of course, you think. That's clearly the right approach. But put yourself in front of a blank page with a similar problem, and suddenly nothing is obvious. The steps that seemed natural when someone else took them now feel impossible to discover on your own. This is why the second principle is essential. You don't understand something unless you can explain it simply, without jargon, to someone who knows nothing about it. This isn't about making things elementary. It's about testing whether you've grasped the essential idea or just memorized the sophisticated-sounding words that surround it. When you try to explain something, really explain it, you discover the gaps in your understanding immediately. You reach for a word you've been using comfortably, and suddenly you realize you don't actually know what it means. You start a sentence explaining how one thing leads to another, and halfway through you discover you can't finish it because you don't see how the pieces connect. These moments of confusion are precious. They're showing you exactly where your understanding is false. Most people avoid this discomfort. When they hit a point they can't explain, they skip over it, tell themselves it's not important, or hide behind technical language that sounds impressive but means nothing to them. But this is precisely the point where the mind that can't fail does something different. It stops and refuses to move forward until the confusion is resolved. It treats every gap in understanding as a structural weakness that must be repaired before building higher. Imagine trying to explain to a bright 10-year-old why ice floats in water. You can't use technical terms they don't know. You can't wave your hands and say it's because of density without explaining what density means and why it matters. You have to think through the actual mechanism, the real reason, in terms of concepts you're both certain about. And in doing this, you often discover that your own understanding was more fragile than you realized. The third principle seems backwards at first. You learn something by trying to solve problems you can't solve yet. Not after you've learned the material, but as the method of learning it. This seems impossible. How can you solve a problem before you know how? But here's the crucial insight. Struggling with a problem you can't solve yet puts your mind in a completely different state than passively reading about the solution. When you struggle, genuinely struggle, your mind is actively searching for patterns, testing possibilities, discovering what doesn't work. And this struggle creates a structure, a framework of questions and attempted approaches. Then, when you finally see the solution, or derive it yourself, or read the relevant chapter, that information doesn't land on passive ground. It lands on prepared ground. Your mind has already carved out the exact shape that this knowledge fits into. The understanding is deeper, more permanent, because you've experienced the problem it solves. Compare two students learning the same concept. The first reads the chapter, understands the explanation, then does practice problems to reinforce it. The second looks at practice problems first, struggles with them, fails, gets confused, then reads the chapter. The second student will understand more deeply and remember longer, even though they spent time failing. The failure wasn't wasted time. It was preparation. This is why the sequence matters so much. Most people try to fill their minds first, then apply what they've learned. But the mind that can't fail is built through the opposite sequence. Attempt, fail, understand, then succeed. The failure creates the structure that makes understanding possible. But there's something even deeper happening here. Something about the nature of real knowledge versus the appearance of knowledge. Real knowledge is a living thing. It connects to other knowledge. It generates new questions. It can be applied in situations you've never seen before. The appearance of knowledge is dead. It's a collection of statements you can repeat, but they're isolated, disconnected from the rest of what you know. The way to tell the difference is simple. Can you use this knowledge to think new thoughts? Can you take two ideas you understand and combine them to reach a conclusion you've never been taught? If your knowledge is real, you can. If it's merely the appearance of knowledge, you can't. This is why memorization alone, no matter how thorough, builds a mind that fails. Memorized knowledge doesn't connect to anything. It's like having 1,000 puzzle pieces scattered on a table instead of assembled into a picture. You might be able to describe each piece accurately, but you can't see what they make together. The mind that can't fail is built by constantly making connections. When you learn something new, you don't just add it to your collection. You ask, how does this relate to what you already know? Does it contradict something you thought was true? Does it explain something that previously seemed mysterious? Does it open up new questions? This active process of connection making is what transforms information into understanding. And it's something you have to do deliberately because it doesn't happen automatically. Your mind won't make these connections just because the information is sitting there. You have to force the connections by asking questions, by trying to use new knowledge in different contexts, by testing whether it really fits with everything else you know. Here's something most people never realize. Understanding isn't something you achieve and then possess. It's something you maintain through constant use. Leave a piece of knowledge unused for long enough, and it degrades. Not because you forget it, exactly, but because the connections weaken. The knowledge becomes isolated again, and isolated knowledge is useless. This is why the fourth principle matters. Keep returning to fundamentals, not to memorize them, but to see them more deeply each time. Every time you revisit a basic principle with more experience, you see it differently. You notice implications you missed before. You understand why it's formulated the way it is. You see connections to advanced topics that weren't visible when you first learned it. The student who races through material once, checking off topics as learned, builds a shallow mind. The student who returns repeatedly to core ideas, seeing them anew each time with more context, builds depth. And depth is what makes a mind reliable. When you understand something deeply, you don't forget it because it's woven into the structure of your thinking. Consider how this works with something as basic as fractions. A child first learns that a half means one of two equal pieces. Simple enough. But come back to fractions after learning multiplication, and you see that a half is also the same as dividing by 2. Come back after learning decimals, and you see it's the same as 0.5. Come back after learning ratios, percentages, probabilities, and each time the concept of a fraction reveals new depths. It's not a new thing you're learning. It's the same idea showing different faces depending on what you can now see. This is how knowledge becomes truly yours, not by collecting it once, but by returning to it, reconsidering it, seeing it from new angles as your understanding grows. And this creates something remarkable, a mind where everything connects to everything else, where each piece of knowledge strengthens all the others. But building this kind of mind requires accepting something uncomfortable. You will be confused most of the time. Real learning, The kind that builds understanding rather than the appearance of understanding lives in confusion. You're confused because you're genuinely thinking about something you don't yet grasp. You're trying to fit it into what you know, discovering it doesn't fit, questioning whether what you knew before was wrong, testing possibilities. Most people flee from this confusion. They want everything to be clear immediately. When they feel confused, they assume they're doing something wrong, that they need a better explanation, a simpler textbook, a more patient teacher. But confusion isn't a sign of failure. It's a sign that real thinking is happening. The mind that can't fail has learned to be comfortable with confusion, to even seek it out. Because on the other side of confusion, fought through honestly, is understanding that actually means something. The student who avoids confusion builds a mind full of statements they can recite but don't understand. The student who works through confusion builds a mind that can think. Here's how this looks in practice. You're reading about a concept that seems to contradict something you learned before. Instead of skipping past this discomfort, you stop. You write down both ideas clearly. You think about whether they really contradict each other or whether you're misunderstanding one of them. You try to find the exact point where they seem to conflict. You work through examples to see which idea holds up. You might spend an hour on this, maybe more. And at the end, either you've discovered that there's no real contradiction, just a misunderstanding on your part, or you've found a genuine error in something you thought you knew. This is slow. It's frustrating. But this is how you build a mind that won't collapse when tested, because you've tested it yourself, constantly, as you built it. The final element that makes a mind reliable is the willingness to check everything yourself. Not because you distrust teachers or textbooks, but because checking things yourself is how you make knowledge your own. When you're told that 2 + 2 = 4, you can accept it. But have you ever actually thought about why? Not just counted objects, but understood what addition means at a fundamental level, why it has the properties it does. Most people accept enormous amounts of knowledge on authority. Their teachers said it, the textbook confirmed it, it appeared on the examination, so it must be true. And maybe it is true, but it's not their knowledge, it's borrowed knowledge. And borrowed knowledge fails when you need it most. The mind that can't fail contains only knowledge that's been personally verified. This doesn't mean you derive everything from first principles, though sometimes you should. It means you've thought about whether each piece of knowledge makes sense, whether it fits with everything else you know, whether you can see why it should be true. You've made it yours through understanding, not just acceptance. This is the difference between education and training. Training gives you procedures to follow. Do this, then this, then this, and you'll get the right answer. Education gives you understanding that lets you figure out what to do in situations you've never seen before. Training creates minds that work like machines, reliable only when operating within their designed parameters. Education creates minds that can adapt, improvise, think. And here's the beautiful thing about building this kind of mind. Once it's built, it becomes easier to add to it. Each new piece of real understanding makes the next piece easier to grasp because you have more foundation to build on, more connections to make. The student who builds their mind properly finds that learning accelerates over time. The student who builds on memorization finds that each new topic is as hard as the last because nothing truly connects. The mind that can't fail isn't built quickly. It's built through patient, honest work, through refusing to pretend you understand when you don't, through struggling with confusion until it resolves into clarity, through making connections until everything you know forms a unified whole. And when you've built this kind of mind, something remarkable happens. Problems that would terrify other people become puzzles you can actually solve. Not because you've memorized more, but because you can think. You can take what you understand and use it to figure out what you don't. You can see patterns, make connections, build solutions from fundamental principles. This is what it means to have a mind that can't fail. Not that you'll never make mistakes, but that your understanding is deep enough and connected enough that you can find and correct your own errors. You can trust yourself to think because you've built something solid, something real, something that won't crumble when the pressure comes. Here's something that doesn't make sense. People set goals all the time. They write them down, they think about them, they tell their friends about them, and then nothing happens. The goal sits there like a piece of furniture in a room nobody uses. What's going on? The answer isn't what most people think. It's not about willpower. It's not about wanting it badly enough. The real problem is that goals and actions live in different worlds, and most people never build the bridge between them. Think about what a goal actually is. It's a description of a future state. I want to learn physics. I want to write a book. I want to be in better shape. These are descriptions, nothing more. And here's the peculiar thing. The brain doesn't know what to do with descriptions. The brain works with actions, with sequences, with patterns of behavior that can be executed right now. When someone says, "I want to learn physics," they're holding a photograph of a destination. But there's no map. There's no sequence of steps. There's just this image of being somewhere other than where they are. And then they wonder why they're not making progress. This confusion runs deeper than most people realize. Goals feel productive. Writing them down feels like you're doing something. Thinking about them creates a little burst of satisfaction, almost as if the future you've imagined is already starting to become real. But that feeling is a trick. The brain can't tell the difference between imagining something vividly and actually doing it, not completely. So you get a small reward from just thinking about the goal, which actually reduces the motivation to pursue it. What you need instead is something entirely different. Not goals, but systems. And the difference between these two things is fundamental. A system is a repeating pattern of behavior that exists in time. It's not a destination. It's a process that happens on a schedule. Every Monday and Thursday at 7 in the morning, you sit down with your physics textbook for 1 hour. That's a system. It has a time, a place, a specific action, and a trigger that sets it in motion. The system doesn't care about the distant future. It only cares about what happens next Monday at 7. Here's why this matters. The brain is extraordinarily good at learning patterns and executing them automatically. Give it a consistent sequence, same time, same place, same action, and after a few repetitions, the system starts running itself. You don't have to decide whether to study physics on Monday morning. The decision was made when you designed the system. Monday morning arrives, and the behavior unfolds. This is how we actually do things in the world. Not through constant acts of will, but through the construction of reliable machinery that operates whether we feel like it or not. Now, building these systems requires understanding something specific about how behavior works. Every action has 3 components: a cue, a routine, and a consequence. The cue triggers the behavior, the routine is the behavior itself, and the consequence determines whether the behavior will be repeated. Most people ignore the cue entirely. They think if they just remember to do something, they'll do it. But memory is unreliable, especially when you're busy or tired. What you need is an external trigger, something in the environment that automatically prompts the action. The most powerful cues are time and place. This is why scheduling matters. Not because time is magical, but because a clock is a reliable external signal. 7 o'clock Monday morning happens, whether you think about it or not. The clock hand arrives at the right position, and that physical fact in the world can trigger your behavior. Place works the same way. If you always study at the same desk, in the same chair, that location becomes associated with the activity. You sit down, and the brain says, "Oh, this is where we do physics problems." The behavior becomes attached to the space. This is why people who exercise at the same gym, at the same time, have much better success than people who say, "I'll exercise when I have time." When you have time is not a cue, it's a wish. 7 o'clock at the gym on Tuesday, that's a cue. The routine itself needs to be specific and small. This is where most systems fail. People design routines that are too ambitious. I'm going to study physics for 3 hours every day. That sounds impressive, but it's probably unsustainable. What happens when you're tired? When something unexpected comes up? The system breaks, and once it breaks, it's hard to restart. Better to design a routine that's almost too easy. 15 minutes, 20 minutes. Something you could do even on your worst day. The consistency matters more than the duration. Do 15 minutes every single day, and in a month you've accumulated 7.5 hours. Miss 3 days, and you've started the process of abandoning the system entirely. There's a principle here that's worth understanding. Small actions, repeated consistently, compound over time in ways that large, sporadic efforts do not. If you write 1 page every day, you have a manuscript in a year. If you wait for inspiration and then write 20 pages, you'll probably wait forever. The brain learns from repetition. Every time you execute the behavior, you're strengthening the neural pathways that make that behavior easier to execute next time. This is physical. Neurons that fire together wire together. The more you repeat the pattern, the more automatic it becomes, until eventually the behavior requires almost no conscious effort at all. But here's something subtle. The consequence of the behavior needs to be immediately reinforcing, at least a little bit. This is tricky because most meaningful goals have their payoff far in the future. Learning physics takes years. Writing a book takes months. The benefits aren't immediate, so you need to engineer immediate consequences. The simplest way is to track the behavior itself. Keep a calendar. Mark an X on every day you execute the system. After a few weeks, you'll have a chain of X's, and there's something satisfying about not breaking that chain. The chain becomes its own reward. Some people use a physical object. Move a marble from one jar to another every time you complete the routine. Some people use a simple notebook where they write 1 sentence about what they did. The specific method doesn't matter. What matters is that there's a small, immediate reinforcement that says, you did the thing. This creates a feedback loop. The cue triggers the routine produces the consequence, and the consequence makes you more likely to respond to the cue next time. After enough repetitions, the entire sequence becomes automatic. You no longer need willpower. The system runs itself. Now, there's a deeper principle underneath all of this. Goals are about outcomes, but outcomes are not directly controllable. You can't decide to have learned physics. You can't decide to have written a book. These things are emergent properties of thousands of small actions accumulated over time. What you can control is your behavior in this moment. Right now, you can decide to open a textbook. You can decide to write a paragraph. You can decide to do 20 push-ups. The immediate action is always within your power. Systems shift your attention from outcomes to processes. Instead of asking, have I achieved the goal? You ask, did I execute the system today? And that second question has a clear, immediate answer. Either you did it or you didn't. There's no ambiguity, no waiting around for future results. This changes the psychology completely. With goals, you're always measuring yourself against something you haven't accomplished yet. You're always falling short until the moment you succeed, and that moment might be months or years away. With systems, you succeed every single day you execute the behavior. The success is immediate and tangible. This isn't just philosophical. It affects motivation in a concrete way. The brain releases dopamine not when you achieve distant goals, but when you make progress toward them. Every time you execute your system, you're creating a small win, and small wins produce the neurochemical reward that keeps you going. There's another aspect to this that's worth thinking about. Systems free up mental resources that goals consume. When you have a goal, part of your mind is constantly monitoring your progress, worrying about whether you're doing enough, feeling anxious about the gap between where you are and where you want to be. This monitoring takes energy. With a system, there's nothing to monitor except whether you did today's routine. Either you studied physics for 20 minutes this morning, or you didn't. That's it. No need to calculate how many more years of study you need. No need to compare yourself to others. No need to worry about the ultimate outcome. Just execute the system and move on with your day. This mental simplification is powerful. It reduces decision fatigue. It eliminates the constant internal debate about whether to do the thing. Monday at 7, you study physics. There's no decision to make. But let's be clear about something. Systems aren't magic. Building a system takes thought and planning. You need to understand your own patterns. When do you have consistent time available? Where can you work without interruption? What cues already exist in your environment that you can leverage? Some people are naturally structured. They wake up at the same time every day. eat at the same time, follow predictable routines. For these people, adding a new system is relatively straightforward. Find a slot in the existing pattern and insert the new behavior. Other people have lives that are more chaotic. Different schedule every day, unexpected demands, lots of interruptions. For these people, building systems is harder, but even more important. You need to find the stable points, the times or places that are reliably available, and build your systems around those anchor points. Maybe you can't control when you wake up, but you always eat lunch. Okay, the 15 minutes after lunch is when you read. Maybe your evenings are unpredictable, but you always commute home from work. Use that time. The specific implementation doesn't matter. What matters is finding the reliable patterns in your life and attaching new behaviors to them. There's also the question of multiple systems. Can you maintain several at once? The answer is yes, but with a caveat. Each system requires a certain amount of mental overhead until it becomes automatic. If you try to install 5 new behaviors simultaneously, you'll probably fail at all of them. Better to build systems sequentially. Start with one. Execute it consistently for several weeks until it becomes automatic. Then add another. The first system is now running on autopilot, so you have mental resources available to establish the second one. Build your life this way, one system at a time, and after a year or two, you'll have a collection of automated behaviors that produce enormous cumulative results. Here's where this gets interesting. Once you have several systems running, they start to interact. The system where you exercise every morning gives you more energy, which makes the system where you study in the evening easier to maintain. The system where you read for 20 minutes before bed improves your thinking, which makes your work system more effective. This is compound interest, but for behavior. Each system produces benefits that amplify the effects of your other systems. The whole becomes greater than the sum of its parts. And there's something else. Systems create identity. When you execute a behavior consistently, you start to see yourself as the kind of person who does that thing. You're not someone who wants to learn physics. You're someone who studies physics every Monday and Thursday morning. That's who you are. This identity shift is subtle but profound. Identity shapes behavior more powerfully than goals ever could. Now, what about the goals themselves? Should you abandon them entirely? Not exactly. Goals are useful as direction indicators. They tell you which systems to build. If your goal is to learn physics, that suggests building a system around regular study. If your goal is to write a book, that suggests building a system around daily writing. The goal provides direction, but the system provides movement. You need both. The mistake is focusing on the goal at the expense of the system, or worse, thinking that setting the goal is itself an accomplishment. There's a final piece to this that ties everything together. Systems work because they align with how the brain actually operates. The brain is not a rational planning engine. It's a pattern-matching machine that learns from repetition and responds to cues in the environment. When you try to achieve goals through willpower and decision-making, you're fighting against the brain's natural operating system. You're trying to consciously control every action, every day, forever. That's exhausting, and it doesn't work for long. When you build systems, you're working with the brain's natural machinery. You're installing patterns that become automatic. You're using external cues to trigger behavior instead of relying on memory and will. You're creating immediate feedback loops that reinforce the behavior. You're doing what the brain is already designed to do. This is why systems work when goals fail. Not because systems are more powerful, but because they're compatible with the way behavior actually operates in the physical machinery of the brain. So here's what you do. Take the goal that's been sitting in your mind like unused furniture. Ask yourself, what specific behavior, repeated regularly, would move me toward this? What time and place could I attach this behavior to? What cue would trigger it reliably? How can I make the behavior small enough that I could do it on my worst day? Design the system. Write it down. Be specific, not I'll study more, but every Monday and Thursday at 7 a.m., I sit at my kitchen table with my physics textbook for 20 minutes. Then execute it. Do it once, then do it again, then keep doing it until you don't have to think about it anymore. Until Monday morning arrives and you're at the kitchen table with the textbook before you've fully woken up. That's when you know the system is working. Build systems like this, one at a time, and something remarkable happens. The life you wanted to live, the one you described with your goals, starts to emerge naturally from the systems you've built. Not because you forced it into existence, but because you constructed reliable machinery that generates the right behaviors automatically. The future you imagined wasn't wrong. You just needed to understand that futures aren't destinations you arrive at. They're patterns of behavior extended through time. Build the right patterns, and the future builds itself. If this made you think differently about how to approach what you want to accomplish, hit subscribe. There's more to explore about how thinking clearly changes everything.